Okay, there we go. Now we're recording, allegedly. Let me point the camera in the right direction. It does. Okay, so I'll start off with the issue in that sensitivity. So what happened is I have 3 different references that I'm using for this course, and all 3 of them are wrong, which is super awesome. And so I ended up going back to this paper from 1969 where they talked about the sensitivity of a bridge circuit. And back then they didn't know anything, like we don't really know anything. So it was a very good match. And basically what ended up happening, I assume, is at some point in time, somebody wrote the wrong equation down, and then everyone has copied it ever since. And they don't cite it because it's common knowledge. So now it's common knowledge that the equation is wrong. So the actual sensitivity, this is in an announcement that it's worth saying, ends up being this, which I'll walk through in just a second. So it's the change in voltage normalized by the reference divided by the change in impedance divided normalized by the impedance. This just comes from, if you write out the equation for VO, right, which on the bridge circuit is just the differential voltage between the 2 intermediate nodes, is which, right, is basically just the voltage divider, because that's the voltage that you get when you have these resistances. Z1 being our sensor is what's going to change. And so if we're looking for the change in that voltage, we take the derivative, right? When we do that, if we're only using Z1 as a sensor, which is the easiest way to keep it simple, which is what we're simulating, right? This whole term goes away because it's a constant. Right? And so I'm left with, and I'm just going to divide BRF over so I don't have to deal with it. Something like that is what it ends up being with the derivative. I forgot how to do the derivative of these stupid that with respect to Z1, but the Z2 comes up as a multiplier. Now, this one can simplify a whole bunch if we just, so this is really getting at the voltage output. It's not quite your sensitivity by itself, but it's getting really close. So what you can do is if you say, well, at balanced bridge, Z1 and Z2 are the same, and for any sufficiently small change, they're going to be roughly this anyways, the approximation holds. And so what you end up getting really is you multiply Z1 by Z2 because they're the same. So you can have that Z1 squared divided by 2 Z1 squared, which is 4 Z1 squared. Z1 squared, you get 1/4, right? That's what we were looking for. That's the sensitivity of a quarter bridge is 1/4. So that's kind of your verification. This at least makes a little bit of sense. And it also makes sense because the sensitivity isn't helped by this term, so it shouldn't be there. And anyways, that's your sensitivity. The fact that this is 1/4 double checks it. Anyways, this equation is all that you really need in order to plot it. You'll be fine.
So what are we doing with the DZs and the Z1?
Oh, this is the Z1 relative to whatever the sensor is at. Okay. Yeah. Pretty sure. If your peak isn't 1/4, then I'm mistaken. But
so the DZ should be just 1/4.
No. So DZ is going to be what you change, right? Because you have to take 2 points of measurement that are kind of close, like the 2 ohm. Yes, exactly. And so what we should see is this plot. right? And this is the balanced bridge situation. So that point should be 0.25, where the x-axis is your K ratio, which is Z1 by Z2, and which is the same as Z2 by Z1. It's just mirrors that. Okay. With that out of the way, let's actually talk. Right, I was saying we were simulating, I think in the lab, I was saying that we're simulating a strain gauge. So let's go ahead and talk strain gauges. Now, what strain gauges are really designed to do is measure force. Now, why do we measure force? Lots of reasons, right? Because force is correlated to and we can measure weight, pressure, strain, and acceleration, right? Some of those are a little bit indirect, right? Because like weight is the same as acceleration in the same equation, right? The force is equal to mass times acceleration. You have to know mass. So it just depends what you know. So if you're measuring weight, you have to use the known acceleration of gravity. Whereas if you're measuring mass, acceleration, and measuring acceleration, you have to know how much the thing weighs or be able to calculate it. Now, you're going to see this in something like, your household bathroom scales. You're going to see it in HVAC systems because these are dependent upon pressure, right? And pressure generates a difference in force. Pressure is always relative, but it's something that you can measure with a force sensor. Something like blood pressure monitoring, right? That's pressure, that's a force. Altimeters and airplanes, again, pressure. You could measure like the acceleration, uses a seatbelt sensor when it should snag. If those weren't mechanical, they are, but right, anywhere you're applying a force, something pushing on something, a difference in pressure, that kind of thing, you're going to want to measure force. The strain gauges just so happen to be one of the most common ways. There are essentially 4 ways that you can measure force. Strain gauge is only one of them in this particular kind. The obvious one is you build a scale, right? A balance that you put something on here, you put something else here, and you see how far the scale moves. That's the simplest one. We don't really use that as a sensor because the output isn't electric, so it's not really helpful. The other ways is we want to measure the acceleration of a known mass. So if we know the mass, measure the acceleration, we know force, right? We can also balance the force against a known electromagnetic force. So if you want to go through EMAG, which I am terrible at, you could create an electromagnetic force and then measure its distance or pressure, the change there against a magnetic force. And you just use math to figure out what that magnetic force is going to be, right? You can also convert force to a fluid pressure, which ends up being really interesting. I may talk like half a lecture about it in the future, but that's how a lot of the early ones were, where they were basically these tubes, and you would have this differential thing, and they'd measure the level as they teetered back and forth, depending what the pressure was, right? And then you'd have the output come out and tell you where the level was on each side. And then the last one, and this is where strain gauges come in, which is you measure the strain produced in a resistive conductor. And it's simple because you are going to have to, sorry, I shouldn't say simple, it's possible, because it turns out that when you change the geometry of something, you change its electrical characteristics, right? And this kind of makes sense, because if you're defining the conductivity of something, it's going to have to do with the surface area, or the area in general, the volume of your conductor, because that's how much charge that it can carry. So when it bends or changes, that's going to change how conductive it is. These changes, unfortunately, tend to be very, very small, but it's measurable using these bridges. Now, the way that you're going to picture this is that if you imagine like a cylinder, right, of like elastic Play-Doh, okay? And so, when you squish it, the sides bulge out, and when if you release, it would go back to the cylinder. Similarly, if you grab it and stretch it, it gets thinner. So what a strain gauge is really just something like this with copper metal. You would then put my drawing skills to use here, right? You just tape it to the cylinder. And when you squeeze it, and I shouldn't say tape, you really have to like glue it. You really need to affix it on there so it doesn't shift relative to the cylinder. What's going to happen is it's going to squish, crunching the conductor together, which in that case is going to lower the resistance because you're starting to push that material closer and closer together. It's easier for electricity to flow. Therefore, the conductance increases. The opposite is true when you grab it and stretch it out, right? So I grab the cylinder, stretch it out. The conductor is going to stretch with it, and it's going to become harder for conductivity to flow, and it's going to become more resistive. Now, unfortunately, and I'll probably end up bringing this up a couple of times, that change is actually very small. It's not very big, which we'll get into magnitudes in a little bit, but this is kind of a tricky thing to measure. If you want an example of it, I actually managed to go find one. So this is, I can pass it around. This one actually has 3 different strain gauges. And what's kind of useful is if you were to put one of these on the other side, you could measure, you'd have a calibration sensor, right? Because you, on one side, you would measure the expansion, and on the other side, you'd measure the compression, and you could calibrate them against each other. But that's all this is doing. So the way you would measure something, like let's say we wanted to measure weight with this beam, we would go get a C-clamp, clamp it to the table. We would then use a weight or a couple of weights to calibrate it, and we hang it on the end here, right? We get a couple of points, clamp this side, weight on this side, it would bend. Then, once we have a couple of points using a known weight, we can use our linear estimation to create a curve, and we can put an unknown weight and measure using the strain, what is the weight? So this is like a real way, if you want to pass around this look, sensor. So the way we measure it, right, is measuring that change in resistance, which means a bridge circuit. Unfortunately, the Freyden book is very, very cursory with strain gauges, which makes me a little sad because they're just like, kind of, here it is, throws out some equation and moves on. So if we look at the problem that we had in the simulation, right, where we had this definition of sensitivity for the bridge, we can ask the question, what is the sensitivity for this sensor? Because the sensitivity matters, right? Because that's kind of how we're going to calibrate it and figure out using that linear estimation, is that the sensitivity is the slope of that line. So I went ahead, I pulled up my IDA book and peeked at it, and it turns out this sensitivity is wrong as well, which is super cool, by the way. And what's interesting is they end up with the right equation, but they do so without knowing what they're doing. And it makes me suspect about a lot of other things as well. So I'm having a hard time with this book, because what it does is it ends up with this nice, beautiful equation. And then it says, you take the derivative of both sides, and then they write the answer after that. And they did not take the derivative. It does not match. So the moral of the story is be careful when looking at any of these books, because I fell sucker to it. It's brutal. So what I'm going to do instead is the smart way, which is what Jeremy was starting to do in the lab last week, which is just look at what it should be. So what should the sensitivity of the strain gauge be? What is it really measuring? Well, we know that the output is going to be a delta R, right? That we know is measuring. So that goes in the top. And we can quickly make the argument that it should be normalized to R naught. What is the initial resistance under zero strain? So that's our output. What is our input? And also, if you forgot, right, the sensitivity is going to be unitless. So that's the other reason, is we know we have to normalize it because Otherwise, unless my output is also resistance, I'm not going to have a unitless quantity. All right, so what is our input? Well, it turns out that we're talking about that deformation. The input is the deformation of that conductor. Specifically, it's the change in length of that conductor, is how much does it change? That's what we're inputting. And then, of course, normalize it to its length. So this quantity here, the delta L by L, is actually what we end up calling, I just forgot the word. I'll figure it out. Anyways, it has this unit of epsilon because there's two terms that we're gonna have to learn, which is gauge factor, and I swear I wrote this down because I always forget. Epsilon. Do you have the book out that I can just peek at what epsilon ends up being called? I really just like delete it or something stupid. That's really funny. Anyways, so we're gonna call this the delta L by L epsilon. They also have this idea that this term in a strain gauge, they actually don't refer to as sensitivity. They refer to it as the gauge factor. Now, if you went and looked at the Freyden book, I don't think they call it gauge factor, they call it SE. And if you go and look at the IDA book, they just use an italics lowercase g. They're all kind of the same thing. It's just a description of the sensitivity of how any given strain gauge is going to function. So
is epsilon the DL over?
Yeah, it's just
Okay, it's that whole.
just that.
And the L and R don't change at all,
Right. Yeah. Yeah. As long as we have small changes, it works for small changes. This loses for any big changes. And what you're looking at, in general, your upper end for just your run-of-the-mill average strain gauge is going to be like a deflection of like 2%. It's not very far. So in a strain gauge, we are talking very small changes in impedance because we're talking small changes in that. And you lose linearity really quickly if you get side out of small deltas.
It's not like this piece of metal.
Kind of. So one of the labs that I was considering doing, I actually think I've got a better one that but we have a bunch of weights down in one of the other rooms that go up like the full weight bench sets. And we've gone through and measured the exact weights. So it's like, it'll be like a 10-pound weight. And you can actually get a lot of deflection on one like that. And that's part of the reason why there's the 3 is because the outside one will start losing sensitivity before the innermost one. Okay. Now, in general, the reason that our sensitivity kind of sucks is because this gauge factor is usually about 2. So it's not very big, and that's for this type of wire conductor. They like to go ahead and describe things a little bit differently and arrange it as delta R by R is equal to, and we're just going to move epsilon up to here, gauge factor, and I'm actually going to write it as G because I like that much. Well, G looks too much like grams, doesn't it? Okay, because I can't draw in italics. Gauge factor times epsilon. So what they're describing here, what they're interested in is the delta R by R. Now, unfortunately for us, if you go look at some of the books, they will interchangeably refer to the gauge factor and delta R by R as sensitivity. They use them as an interchangeable term and it drives me crazy, but this is not the sensitivity. The best that you can do it is, I think copper is just under 2, right? We like copper, it's cheap, it's easy. If you want to do the best you can, one of the best materials you can use is called platinum iridium. Right, it's a mixture of the two. It turns out that both of them are very, very expensive. And so that's kind of why they don't usually use it. And the only thing you go is you get a gain factor of 6, which is not that much of an importance for massively increased costs. So that's why we kind of get this issue here.
So something like this one with the 3 gauges is probably better or something.
The outermost one will strain more, right?
I mean, like if you add all of more or less, like you're gonna have to figure.
You can't quite just add them, but yes, you increase your sensitivity because you increase the range of strain that you can measure, and so the sensitivity scales to the range, more sensitivity. Okay. So now this resistance though is not just strain, right? Because all we're measuring is the conductivity. We're not actually we don't have like a microscope that's measuring the length. We're just measuring how that resistance changes. So unfortunately for us, any temperature changes are also going to change conductivity. So what we end up with is saying that I remember now, epsilon is just strain. That's why I didn't write it down, because it is just strain, which is delta L by L, the definition of strain. I remember now. Okay. So in this case, if there is no strain, there is no change in L, then R naught is just R, right? So this is your kind of basic equation, unless you want to go ahead and say that it is relative to epsilon, the strain, and temperature, right? Because increasing temperature or decreasing temperature affects how conductive something is, which is why, if you know about superconductors, we super cool superconductors because colder is more conductive. Same reason as the string gets more conductive as we squish it together, right? Things just get closer and closer together. It's easier for electricity to bounce along. That concept is actually going to keep coming up with different kinds of strain gauges as well. So this one gets a little more, I won't even say complicated because it's not really. I have 2 different forms of this that I have to kind of decide on. Yeah, okay.
That little g is the gain factor.
This is the gain factor. See, all of my equations are in G because I typed it.
Gauge factor.
Gauge factor, which is that is also kind of gain because sensitivity is kind of the sensor's gain. Anyways, so I'll get to alpha in just 1 second. It's not R of epsilon, this is R. I mixed 2 equations there. So what just happened there, why I wrote R of epsilon is because if you take R of epsilon multiplied by the temperature, that's what we're doing. And then the second equation that I wrote down is just this, where we're taking R naught, which is, this is R of epsilon, right? Function of strain. So we're really ending up with a multiplicative error at our input, right? That is the multiplication of the effective strain by the effect of the temperature. Alpha is what we call the TCR, which is really just your temperature coefficient of resistance. This thing, and I will always make fun of mechanical engineers for this, my younger brother is a mechanical engineer. I always like to call them table engineers because they like to go and look things up in tables. You're never going to expect it to know alpha. So they spend a lot of time. So you're going to go, like if my metal is copper, I need to go look up what is alpha for copper, right? To determine how this change in temperature is going to affect my resistance. Okay, so this guy, this one right here, he's going to come up. I'm going to have you guys tinker some with this in a little assignment. So write that one down. You guys see orange? I can't tell.
Yeah, it's hard.
It's
Green better?
Yes.
Or I can run and find a different earth color. But
There's some reds over here too.
Oh. Are the good ones hiding? Is that what's happened?
You gotta find those refills.
Okay, there we go.
So for the R epsilon.
Yeah.
So we're saying that R, oh, sorry, never mind. I didn't see. Okay, never mind.
Okay, no worries.
Temperature coefficient of resistance.
Yes. Yep, the TCR. So unsurprisingly, there is actually more than one kind of strain gauge. This one will describe any of this wire type, which is really the most common, right? Because it's super cheap to make. The simplest, you could even go simpler. You could use just one wire, but the folding it back over means the length changes more with a smaller sensor, right? Because every fold in that changes. So that's why we don't just use one wire. We're actually increasing the amount of delta L that we're getting. In general, they tend to make these, like if you were just go buy one, they're somewhere between 100 ohms and 1 kilo ohms is kind of your nominal resistant range. And as I said, your gauge factor is like 2 to 5 maybe is your typical. And unfortunately, and this is why things are awful, I'll draw this delta, your delta R by R in this kind of wire measurement system ends up being something terrible like 5 milliohms per ohm. It's very small. You don't get much change in resistance, which means at the output, your change in voltage is also very small. So my plan at this moment is to next, my phone, I need time, I was going crazy. Next time, I'm going to kind of introduce instrumentation the way I should have, now that I understand better how to teach this class. And we'll talk about how we hook circuits up to these bridge circuits, because you're not going to rely just on 1/4 gain of a bridge circuit, right? That sensitivity is insufficient for gain. So we want to be able to think about it in terms of how do we measure these very small changes in resistance using something like an ADC, right? So that'll be the next lab, but I think that one has to be next week because next class, Thursday, I have to talk about those circuits so that we're all on the same page with that, so that I don't just assume that you guys remember anything about op amps, right? So that's where we'll go from there. Now, the one that's been passed around, I don't know where it ended up so far. Is this, guys, have you seen this yet? Okay. That kind is not the only one. You'll see a lot of different versions of it that will do things like they'll put in an arch like this and start measuring them, and so that you can start getting angular strain, right? Because unfortunately, if I measure strain on that guy and I were to do what I said and hang a weight on it, if it wasn't perfectly balanced and it twisted at all, that is also strain, right? It doesn't differentiate between the direction of strain. So adding additional directions can give me higher accuracy in the amount of strain in the direction that I'm wanting. The other way that we deal with this error is, notice how it's really long in one dimension and not the other. that is a nice mechanical way of dealing with these errors, is because it's very hard to torque that this direction and very easy to go this direction. So therefore, we have a mechanical method of ensuring that we don't get kind of directional strain. And you'll see full 180-degree versions that will measure the strain in any direction. Yeah, and these sensors are kind of, I just remembered one of the cool ones is they'll put them on like flywheels for high torque systems to make sure that they're not about to explode and kill whoever's working with that engine, right? That's really common because the metal started to form long before an explosion. And so if you can measure super tiny changes in the delta R, you can shut the system down before catastrophic failure. Okay, we don't, however, have to stick with this type of wire gauge. There is a different device that we're very familiar with. It turns out that semiconductors also change impedance with strain. So if you bend silicon, doped silicon, it changes its resistance. So if I have a very basic model where this little pocket, right, is my doped silicon, and I just have two simple contacts, there's going to be some resistance in here. And as it bends, it changes as long as my voltage across does not change. So this is very sensitive to changes in voltage. So like if you have power supply noise, for example, or reference noise, it's very problematic because semiconductors are nonlinear, right? Unless they're very carefully designed, it's going to have a nonlinear response to a change in voltage across the semiconductor. So we want to stay in about the same area and measure only that strain. So what's super nice is that silicon, well, for one, can have gauge factors up to about 150. And this is as of like 2008 or something. So I don't know how much better they've gotten since then. But the cool part is they can actually have negative gauge factors. They can go the other direction, right? And it's just how you dope it. That's all that you need to change in order to change the gauge factor. You can't have a negative gauge factor with a passive wire. The downside is, and if you've designed anything in silicon, this is kind of obvious, these become very, very sensitive to temperature. So there's this phenomenon that we'll get more into later when I talk about temperature sensors, but there's this problem of self-heating. So if this resistance is high, it can actually heat up the silicon and result in a different measurement. And when I say high, the temperature coefficient of copper is 10, right? Alpha is 10 for copper. The temperature coefficient for doped silicon is 90,000.
Oh.
So that little alpha does very little to most of these copper, but does a whole bunch to silicon. So when you're deciding on what material to use, if you want really good sensitivity, you choose silicon, as long as we're confident in our ability to isolate from temperature or correct for it using a bridge, which this is going to be my next lab is the plan. I'm going to have you guys build the bridge that you used in the simulation. And then we're going to build on an instrumentation amplifier so that we can measure it. And then I'm going to have you guys actually do some measurements where you're going to start by measuring just known weights. And we're actually not going to use a strain gauge. We're going to use a force gauge, which I'll talk about in a little bit because they're a little bit easier to work with. And you guys will measure that change in resistance. You'll calibrate it about little calibration weights so that you can know what it is. Measure some, then use it to measure some unknown weights. And then we'll start playing with the temperature. I bought little heating pads that will set underneath some of the temperatures, and we'll use the H-brid to compensate for the change in temperature, right? So we'll get some hands-on measurement for this type of bridge circuit. Okay. So the The other issue, the final issue that you have with silicon is that its transfer function is nonlinear. So unless you're having very small deltas, you can run into a problem. So you're going to need to, generally the data sheets for these ones are better, but you still have to be very careful with your transfer function and your calibration. Okay. So next up, I'm going to talk force sensors because that's what we're going to use. Now, force sensors can operate on the same principle, right? I can actually use, as I mentioned, a strain gauge as a force sensor. That works just fine. But there's also a cooler way to do it, in my estimation, which is, actually, let me draw one up here. This one's kind of, I love these kind, and I almost did a project with it. So they'll have a button type force sensor, so something that you push on top of. And the way that it works is they have some sort of metal rod that will stick through like that. And as the pushes down, it might even just have like a smaller contact like so. And so as you push down, it gets deflection, and then your strain gauge would be like here. And it would measure that deflection as you push that button. So that's like how, that's one way that you would use a strain gauge as a force sensor, right? And as long as you know the acceleration, which is gravity, right, then you can measure like the mass. The cooler way, the one that I really like, and it's the kind that I have misplaced somewhere. Here we go. This is what you guys will be using. So this guy, it's instead of having to take the time to affix it to a bar that we can bend and deflect like that one, this one is just literally, if it squishes, it becomes more conductive. Okay, really cool effect. Now the question is, how do they do that, right? Well, if you take two metal contacts, which we call electrodes in general, right? So these two are going to be metal contacts, and you fill the middle with a printed material, so like 3D printing or deposition, however you want to do it, where these little globs are conductive and the intermediate substrate is not. So then when it's just sitting there, it's going to have some resistance that is arbitrary, right? You can kind of design it statistically, but you're not going to be exact, because it's going to, if I apply a voltage here and say, we'll just use ground here, right? Well, the current can jump little bits through diffusion. So like this is just traditional flow because these two globs are connected together. Specifically, it is called just conduction, right? Then if they're close, we can, but not too close, you're going to have hopping is what the phenomenon they call it. And then lastly, if you're super close but not quite there, they call it tunneling. And you don't need to, I don't think I'm going to test on those, but it's just kind of an interesting effect. Anyways, what happens is this is a bit of a squishy gel. And so when I push on it, what happens is all these little black globules squish closer and closer together and become more and more conductive, because they go from having to hop long distances to getting closer to their diffusion until they contact and it's conduction. The more of them that can make contact, the higher conductivity you get. So I think, I'm not 100% sure because the data sheet is atrocious. This little guy, I believe, has a nominal resistance of 300 ohms. So we're going to pick resistors of 300 ohms, right? And we're going to solder up little wires onto this guy, plug him into a bridge circuit, and put little weights on him and measure how things change. Hopefully it works. Hopefully it works. I haven't done it. I'm going to try and do it before I do the lab, which hopefully I have the weekend to do that, but we'll see. The cool thing is, again, these are actually kind of linear, linear-ish. The curves, well, Can be. I don't think these ones are linear. I didn't spend enough money to buy a linear one.
This costs 50 cents a piece.
Something like that. I didn't pay too much attention because the department pays for them using your guys' course fees, which is really cool. But yeah, I'm not gonna do that. So I was gonna, for fun, go through the derivation of the sensitivity for the wire kind, but I don't think I'm gonna do that because it's messy. Yeah. What I will do is an example problem, the kind of thing that I should probably post some homework and make you guys do, just to hammer home the math side of this, so it's not just a purely, purely hands-on course. I like the hands-on aspect, but I don't want to be just hands-on. So we're going to consider a strain gauge. And we want to do things like, I'm going to erase this equation. No, I'm not, because I need it. This. So for A, we need to find R at 25 degrees C. For B, we need to find R if the strain epsilon is equal to 1 milli. And C, we're going to estimate the gauge factor. I haven't done this part yet. We'll see how it goes. Done the other two. Okay, so the things that we need to know are things like, what does the strain gauge look like? How many coils does it have? We need a lot of information to start with this sensor, right? We have no hope if I say there's a strain gauge, calculate these. So first off, it is 5 micrometers thick. The sensor is, let's see. I forgot one equation for you guys actually, which is really kind of funny. I'll do it over here. This is the downside that I didn't do the derivation for you where the sensitivity comes from, because if you look at the resistance of a conductor, to make sure I get this right, L by sigma S. Okay. And the last thing that we need to know is that the thing is made of this material called constantin. Constantin is really cool because it is very temperature resistant. So obviously, when we're given the material, we're going to have some kind of lookup table for various things. Oh yeah. Seven, 8, 9, 10. Okay, this is our strain gauge with a length of 25 millimeters and this length. So that's this length, and that length is 0.9 millimeters, right? Because we need to know the length to normalize anything. We also need to know the length in order to calculate the resistance, right? Because sigma's conductivity, we need to know how long it is to end up with the total resistance. The longer it is, the more resistance we end up with. Okay, how do we calculate the length of this guy? We'll just go through one step at a time. Yeah, Yeah, we just add them all together. So L is equal to 10 times, right? I mean, 10 of them, 25 mil, plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 21. I think, yeah, 9.
So you don't play the lead.
No, they'll these wire leads will usually be highly conductive is the ideal situation, or they will tap out right there in the diagram. If I were to put this on a homework or quiz or something, then I would not fault you for either 9 or 11. I'm not going to be that picky. Okay, and that ends up, if I do the math, 9 times 0.9. It ends up, I'm just going to skip so I don't spend 100 years, and it should be that, I think. Someone can check me if they're in doubt.
Those are millimeters,
Yes.
Yeah, so the 25 milli, 9 milli.
right? Like, that's not just meters.
Yes,
MN.
I would, yes.
I'm like 25 meters is kind of long. I'm
Huge.
assuming it's not that, you know.
Okay, oh yeah, I forgot because I didn't do the derivation that I was gonna do. This S the cross-sectional area, right? Which makes sense. That's the thing that's missing, right? Is how long is it? How conductive is the metal? How big is it? Because the bigger you make it, the more conductive it gets. And it makes sense that it's on the bottom because a big number on the bottom makes a little r. Just like a big conductivity makes a little r. Okay, so now we can go ahead and calculate S. Well, S is going to be 5 micrometers deep, right? And oh, the number I didn't get you here is they are 0.2 millimeters wide. Tons of information. You have so much information about these things to calculate them. Right. And so when we think cross-sectional area, well, they're 5 micron deep and 0.2 millimeter wide. We multiply them together and we get something like 1 nano. And I don't mean nanometer squared, I mean 1 nanometer squared. Right, those are two very different numbers. Okay. Now, all of this is kind of assuming we know some originating temperature. All right, so then finally we can calculate R. We know how long it is. We can look up the conductivity on a table, and we calculated the cross-sectional area. If you go look up at a table, this is like trivial, and I would probably just give this to you in an exam, right? Or like have a table with the values. The sigma for our material is 2 times 10 to the 6th. That should go here, but I've kind of divided myself up. So we plug those numbers into R and we get the resistance, right? This is going to be our nominal resistance. Do that down here. So the resistance would be that, and if the math is right, R should be like 129.05. Oops. Okay. We're going to need alpha. All right, let's give you an alpha that is equal to 1 times 10 to the negative 5. All right. So finally, so I've walked you through that. None of this is too hard, right? This is like geometry. This geometry and tables. You are now mechanical engineers. Except for fluid dynamics. I always give those guys a pass. Now, let's calculate R at 25 degrees C under no strain. You have everything you need.
Under those
We
guys?
just did that without compensation.
So temperature, we're going to fix at 20 degrees C for all of the conductivity and everything else.
I mean, that R that we have,
This R is,
is that 20 degrees?
So it's- Okay. So that's like T naught, right?
yes, that's our R naught. That's our nominal value. That's where we start. You kind of always have to make an assumption about starting temperature. And then typically if you were like doing this in a lab environment and you needed everything to be precise, you would do the measurement inside a temperature controlled viewer.
So is that T or T naught? That 20 degrees? It'll be our T.
Yes, T naught is our initial, yeah. So anytime we say naught, we're talking nominal values. So initial calculations.
What are you saying for the G?
We don't know.
G is. Change it out. Oh, wow.
Yeah.
But we don't need to know, right? Do we see why we don't need to know G yet?
I don't know what the strain on the.
Exactly. There's 0 strain, therefore G times 0 is 0, 1 plus 0 is 1. We don't need to know G yet.
We need it
So we're just
for-
finding what it's at.
for E though, right?
Just for the temperature. I got you. Yeah, so we just solve it.
Ideally, we don't want to change one or the other. We will.
Yeah. Guess I get
What?
I'm assuming you have all the answers.
Yeah, but I want to go through it just so that when we assign something, right?
We got to the point where like, I got to the point where you just plug it into a calculator, but
Okay, yeah. If we're to the point where we plug it into a calculator, we should hopefully end up with what part are we on? A?
yeah. So you just do 1 point, what is it, like 405 times.
Yeah. So this is actually really kind of funny because if you have any sort of sig fig tracking, your multiplication factor, this guy, is 1.5, which means that your resistance at 25 degrees Celsius is the same as your resistance at that. Right. So it's saying that for Constantin, it has a very low temperature coefficient, right? It has a very small change in resistance due to temperature. So fortunately for us, I think the heating pads I can do like 60 degrees C over room temperature or something crazy like that. So don't touch it, they might be hot, I don't know. Anyways, yeah, so you can do the calculation again if your alpha gets much higher, right? We can do the calculation like, let's pretend that the strain gauge is actually made out of doped silicon and its gauge factor is 90,000 instead of nothing. Okay, now this one is where it gets a little bit more fun, is what happens if if epsilon is equal to I don't 1 meter. I mean, I'll just draw it this way because it's 1 milli unitless, essentially, because strain is delta L by L, so there's no units, right? So that's where we start, is we start with this idea that the strain is defined as delta L by L. Now the strain in a strain gauge is going to be applied this direction, okay? Because we want to take advantage of the length as much as we can. So when we squish it or stretch it, we want that to be our L. Fortunately, by folding it back in on itself, we've multiplied it by 10. So our L is equal to 10 times 25 milli, which is 0.25. Delta L is what we're looking for, right? That. So now we can calculate our delta L. How much is our length change? Because we've been given strain, which is delta L by L as 0.001. We've got our L. We end up with delta L is equal to, yes, micro. You guys are units. Just kidding. Better have it. Yes. So that's our change in delta L under this strain. Okay, so the next thing that we have to do is, and this is really annoying actually, is start looking at the volume, because the volume is unfortunately what's going to start doing the deformation, right? Which is tied to our cross-sectional area. So I know this one's really terrible. We're gonna have time to do this one. I don't even. Yeah. So if I give you that the volume is linked to V naught by delta L, which is equal to so here we're using the L. Shoot, I forgot. This is 250, 0.25 milli. How did I do this wrong? Because this is 25 milli, so that would be 250 milli. That makes sense. Okay, right. So L is 250 milli. The cross-sectional area, S, we can plug in, and we have our delta L, which is 250 micro, right? So S tick ends up just being this is an annoying, stupid equation that I would give you. I'm not gonna keep that one secret. But it's just relating how much it changes as you squish the volume, because the volume of the material doesn't change just because you squished it, right? Okay, and then we can just plug that number back into our new R, right? We have our new S because it's changed my cross-sectional area. We get a new R, and new R is 125.25 ohms. So we've had a whopping change of like 4 ohms. Did I do a number wrong here somewhere?
No, I was just asking you, use S tick to.
Yeah, that's tick for the resistance.
Okay.
And the conductivity won't change. Yeah. I kind of simplified one of these, I think, because, let me double check, because it doesn't really matter. The value doesn't change because this is really, this is like 0.25025, like is the initial L, but that point zero is extra 0.25 is just insignificant.
I got 129.7 for the new R.
Go here.
8.258 divided by sigma times by S.
0.25, so 0.250.
No, 0.2581. I got the same thing.
Okay.
Yeah, I was gonna say, why did we change the L from 0.2581?
I think on these ones, we should just put like L prime.
Yeah, you probably need, because this L is the 0.250,
Right.
and then the L plus delta L, right, is the sum of that. Okay, and so you should, what did you put as your S? Here,
So if you use the
1 nano?
Yeah.
Okay,
If you use the 0.250 for your L, we get your answer. So I think we're okay.
oh, this one,
Yeah, if we use the new,
this term rather. That one term, or which one?
well, I went on here as prime, so I'm not.
It's for your L, right? Because you're saying that the 0.250 is when it gets smashed down, right?
That's
You're
your,
basically taking away the 0.9 that we have there on the side of it, right?
yeah, this one doesn't
So it gets
matter.
disregarded and then it just becomes 0.250, and then that's the new value that we're checking.
Yes.
Okay.
But there's the one thing that I'm trying to figure out that I have in this is why they, does it change? How much does it change if you use the, so I was just approximating L as L, which is probably is wrong. So how much does it use it if you do this one, the sum of these two as 0.25025? Okay, I may have skipped a step because it's
Yeah. 1.03.
sorry. repeat. The book may have skipped a step and I may need to figure out what's wrong with the book.
Oh.
Trusting the example again. What number do you get again? Just tell me.
1.03 times 10 to the negative 9.
Okay, so that's our new S prime, right? And then
It should
We'll
have
plug that one into
less
the-
cross sectional area. I think that's prime, okay.
Yeah, S prime's fine.
You get 125.25 if you use delta.
this, so using this, we get that value, 125.
Yeah.
Okay, so apparently this is non-negligible. My bad.
Okay, yeah, 'cause I got.
So the 0.25025 is L plus the.
Yeah.
Where do you get the delta L from? Just
The delta L is coming from, where do we calculate it?
oh, okay.
Okay, you guys are verifying that this works, and I should not round numbers. Okay. So we get this very small inconsequential change, and then hopefully we can use the old equation of the dr shoot.
GF times.
Okay, louder. Let's get it.
Equals GF times epsilon.
Oh, equals GF epsilon.
Yes.
And what we need is epsilon. Oh, wait, sorry, we have epsilon. We need the G. So what we're looking for is epsilon is equal to dr by r times 1 by the strength. Which we have the delta R, 125 minus 129, right? We have R, which is our nominal resistance, 129. And then we have epsilon is defined by here. Strength. Oh, yeah. Should just dump out a number, right? I don't think there's anything tricky. Don't worry, I'll post this example to go cry your brains out over his thing, and it'll be a couple of questions. The exam is, I have to do an exam, it's on the syllabus, it's unfortunate. I'm gonna make it like any of the practice problems I give will be close to what shows up on the exam. I'm not gonna put twists on it because I'm this close to just like not doing an exam. I just don't know I don't know how I can get away with that with my syllabus, right?
Make it another one.
Make it a big lab,
Make it.
hands-on.
Hands-on.
Can you make a change to the syllabus if we all?
Yeah, we can, but I might get in, this is a grad level class. I might be able to get away with that.
You guys have already do that.
Well, I'm reducing the exams so that you don't have to stress about them, because there's this weird balance between the number crunching, oh yeah, like 1% or something. No, I'm just worried about like when accreditation comes through, they ask us to show how we know that you guys know things. And so if I'm like, the exams are with 1%, it doesn't really help. Whereas if I show them the exam and the range is like 85 to 100, and I'm like, I don't know, they did really well. This is the first exam that I had to write from scratch. Oh no, that one won't be really getting me in trouble.
So it was a homework. It's exactly like an exam. Different numbers.
I need a little bit of variation in the class. Anyways, that's 6:15. You guys are free to go. I will post this example so that the chaos of ordering. I don't know yet. I'm gonna figure out where I.
That's the easiest.
So that was that's it.
This one's gonna be like
All
your.
over.
Look, I really would love to see 85 to 100.
What's up to say?
Apparently everything is on anyway, so.
Let me stop this.
I was gonna say, how are they?